So to just review here, when we talk about exponential models, we talk about situations where a quantity is increasing or increases or decreases at a rate proportional to the amount of quantity present. So when we're looking at a quantity y is equal to y of t, it is said to be an exponential growth model if it is increasing at a rate proportional to the amount of quantity present. It is said to be an exponential decay if it is decreasing at a rate that is proportional to the amount of quantity present. Thus, when we talk about an exponential growth model, when you're looking at the differential form of an exponential growth, you guys are used to looking at your exponential growth or decay models in the form of y is equal to c times e to the k times to the kt power. The differential form, or the derivative, of your exponential growth is going to be your dy dt is equal to k times y. And again, to be exponential growth, the constant has to be greater than 0. All right, so remember, this k value has to be greater than 0 when you're dealing with an exponential growth. So when we're talking about an exponential decay, it still has the same general form when you're looking at an exponential decay equation. Y is equal to c times e raised to the kt power. The differential form is still in the same form as the growth. Your dy dt is equal to k times y. However, your constant is less than 0. The constant is negative. All right, so again, that's what determines whether you have a growth or a decay. It goes to the constant rate of decay, whether it's a positive or negative number, that k value. That constant k that determines whether or not you have a growth or decay, it is called the growth constant or the decay constant. It may also be referred to as your proportionality constant. So if you see that phrase, your growth is proportional, that is also another way for them to tell you that you're dealing with an exponential growth or an exponential decay model. So for these problems, when you're given the differential equations, remember what we did back in section 8.1, we used separation of variables. When given your derivative, we use the separation of variables to come up with the actual function. The same thing we're going to do with these differential form of your exponential growth or decay. For example, given your differential form of your exponential growth or decay, dy dt is equal to k times y. So what we want to do is we want to solve for y of t. How do we use our separation of variables? What's going to be the first step? I know it's been a while. We're going to divide by y, and then we're going to do what? Multiply by dt. Remember, k is just a constant. That's that constant growth or decay. Then what do we do to both sides of this equation? We're going to integrate. So the integral of dy over y is going to be the natural log of y is equal to what? K times t plus your c. Don't forget your c. Yeah, some of you on your test forgot the c. I know. What are we going to now do to solve for y? Because remember, the idea is you want to solve for y. Raise both sides to the base of e. Remember, kt plus c is in the exponent. So e raised to the ln of y is just going to be y is equal to e raised to the kt plus c. We talked about this when we were doing our separation of variables. Remember your properties of exponents. When do you add exponents together? When you do what with your bases? When you multiply them. So this is equivalent to e to the kt times e to the c. So another way to write this is going to be, what is e to the c? E to the c is just a what? Constant. So C times e to the kt. And remember, that is your exponential growth or decay model. All right, so any questions on using separation of variables to help you solve for an exponential growth or decay model? Remember, graphically, when you're dealing with an exponential growth, again, you're dealing with an equation in the form of y is equal to c times e raised to the kt, where k is greater than 0. Remember, this is what the graph of an exponential growth or decay model is going to look like. Remember, you do have horizontal asymptotes for exponential growth and decay. Where is the horizontal asymptote? It's at y equals 0. 0. It approaches 0. Again, that graphically, when you're dealing with an exponential decay, you're still dealing with the model in the form of y is equal to c times e raised to the kt. But remember, your k value is less than 0. And again, graphically, your decay models look something like that. So any questions on, given the differential form of a growth or a decay, how you can solve for the differential equation? All right, so now let's just take a look at some examples. And these examples, a lot of times you did back in pre-calc. So let's take a look at example 1. Suppose that you have a town of Grey Rock that has a population of 10,000 in 2006 and a population of 12,000 in 2011. And again, assuming that we have an exponential growth model, in what year? So again, we're solving for time. Will the population reach 20,000? So anytime, this isn't dealing with the differential form, you can simply just use your model of y is equal to c times e raised to the kt power. You don't need to use the differential form. So the first thing you have to do with any of these problems is you always have to find the growth constant or decay constant. So you always have to find the k value first before you can actually answer any of the questions. So the initial population reading they're giving you is that in 2006, the population is 10,000. Then 5 years later, in 2011, they're telling you the population is 12,000. So the initial population reading they're giving you is in 2006. So in order to solve for k, I'm going to plug what I know into my exponential model right here. So again, in 2006, I've got that initial population of 10,000. Remember, C is my initial amount. That's what the C represents in this particular model. That's your initial amount. So my initial population is 10,000. So what I'm going to do is I'm going to take 12,000, set it equal to 10,000, times e raised to the k times. Well, what's the difference in years between 2006 and 2011? It's going to be how many years? 5. So just remember, this C value in this particular model, that is your initial amount. So any questions on how I'm going to solve for k? What's the first step here to solve for k? How am I going to start getting k by itself? What's the first step? Divide by 10,000. Did I forget a 0 here? Yeah. So 12,000 divided by 10,000. So that's going to be 6/5 is equal to e raised to the 5k. Then what? Then I'm going to do what? ln. So I'm going to take the natural log of 6/5. And when I take the natural log of e raised to the 5k, that's just going to be 5k. So then finally, to get k by itself, I'm going to do what? I'm going to divide by 5. So then k is equal to the natural log of 6/5 all over 5. Now hopefully your pre-calc teachers, if this was a calculator question, which it's going to be, told you to do what with this particular value in the calculator? Store it, exactly, store it. You don't want to round it to 3 decimal places. You want to make sure you carry it out to as many decimal places in your calculator's memory. So what you want to do, if you remember on your calculators, the store button is located right above the on button. So what you want to do is you want to type in that natural log of 6/5, make sure you close the parentheses, and then you're going to divide by 5. So type in the value first, then you want to hit that store button, which is located right above on. Now, you have the whole alphabet on your calculator. If you look on your calculator screen, you have the whole alphabet. But again, the quickest variable to store this in is just to store it in for X, and then hit enter. Because what the calculator has now done, it's taken this natural log of 6/5 and divided by 5. It's actually taking this out to over 100 decimal places. You're not seeing the 100 decimal places, but that's what it's in the memory. All right? So any questions on how I stored that particular value in the calculator? A lot of the problems, these can be calculator or no calculator questions. If it's no calculator, obviously you have to leave that K value in exact form. All right, so any questions on that? Now that you know K, you can actually plug the values that you know into this particular equation to help you answer the question. So Y is equal to my initial population of 10,000 times E raised to that natural log of 6/5 all over 5 times T. So you first always have to find that K value and then write that exponential growth or decay equation. Now you're actually ready to answer the question. In what year, so what variable am I solving for this equation? I'm solving for what? T. Will the population reach 20,000? So what am I going to do with this equation? I'm going to set it equal to what? 20,000. So 20,000 is equal to 10,000 times E. And now what I do is I just take that K and I circle it so I don't have to copy that value over and over again, because that K value is what I have stored in the calculator. So what I do is I just write K and I kind of circle it to remind me that that's stored in my calculator. You guys go ahead and finish and solve that for me. Year. So what do I have to do with this 19.009? I'm going to add it to what? 2006. So it's going, the population is going to occur at some time in the year 2025. So at some point in 2025 is when this population will reach 20,000. So any questions on that? Kind of ring a bell solving problems like this, I hope a little bit. You also dealt with half-life problems. Remember, we talk about half-life, we're talking about the time it takes for half the element to decay. So, for example, polonium is a radioactive element with a half-life of 140 days. Make sure, guys, you're really careful about your units when you're dealing with half-life. Again, assuming that 10 milligrams of the element is placed in a lead container, Y of T is the number of milligrams present T days later. So it's telling us how many milligrams are actually going to be present. So they're asking me to find a formula for Y of T. So again, we're following our rule of exponential growth and decay. So the model I'm trying to write is Y is equal to C times E raised to the KT power. So what is my initial amount of polonium? 10 milligrams. So Y of 0 is equal to 10. Well, they're telling me that the half-life is 140 days. So after 140 days, how many polonium is going to be remaining? 5. So just like we did in the previous problem, the first thing you have to do in order to write this equation, your first step is you have to find K. So for all these problems, if they're not giving you that constant rate of growth or decay, you have to find the K value. So I'm going to take the 5, set it equal to my initial amount of 10, times E raised to the K times 140. So now to start solving for K, I'm going to divide both sides by 10. So I have 1/2 is equal to E raised to the 140K. What's next? ln. So I have the natural log of 1/2 is equal to 140 times k. Then I'm going to divide by 140, so the natural log of 1/2 divided by 140 is equal to k. So now that I know what my k value is, I can go ahead and I can set up my formula or my equation for y of t. So y of t is equal to that initial amount of polonium, which was 10, times e raised to the natural log of 1/2 divided by 140 times t. So any questions on finding y of t? So now for part B. How many milligrams will be present after 10 weeks? Am I just going to take 10 and plug it into that equation that I wrote for t? No. What's the problem here? Yes, exactly. The question's asking me after 10 weeks, but remember, my model is given in terms of days. So my t value I'm going to have to plug in is going to be 70 days. So then y of 70 is going to be equal to 10 times e to the ln of 1/2 over 140 times 70. So go ahead and answer that question for me. We all end up with about 7.071 milligrams. Okay? Now take a look at part C. Now remember what the model represents. The model represents the number of milligrams of polonium that's present after t days later. The question in part C is asking us for how long will it take for 70% of the original amount to decay. How am I going to answer this? It's going to be 0.3 times my what? My original amount, which was what? 10. So what I'm going to do, remember, is to figure out the time where 70% of the original amount to decay, I want to know when is there 30% of the original amount present. So I'm going to take 0.3 of 10, set it equal to 10, times e raised to that natural log of 1/2 divided by 140 times t. You guys go ahead and solve for t for me. Questions. So example number 3 is a no calculator question. So we have bacteria in a culture at a rate proportional to the number present. If the number of bacteria doubles in 3 hours, so it's very similar to the half-life problem. Instead of giving half-life, they're saying it's going to double in 3 hours. In how many hours will the number of bacteria triple? So notice the answer choices are all given to you in exact form. So again, instead of being a calculator question, they may ask you questions like in terms of a no calculator. Again, problem is you're still going to have to find the k value first before you can answer the question. So for all these problems, if that constant of proportionality is not given, you've got to find the k value. So when they say that it's going to double in 3 hours, again, if c is my initial amount, then I can set this equation equal to 2c. So in 3 hours, I'm going to have double my initial amount. So 2c is going to be equal to c times e raised to the 3 times k power. So then I can divide both sides by c, so 2 is going to be equal to e raised to the 3k. What's next? ln. So ln of 2 is equal to 3k. So divide by 3. So k is going to be equal to the natural log of 2 divided by 3. So now the question's asking me in how many hours will the number of bacteria triple. So I know that I'm going to solve for t. So again, to solve for c, I set it equal to 2c. So if I want to know in how many hours this bacteria will triple, instead of setting it equal to 2c, I'm going to set it equal to what? 3c. So 3c is going to be equal to c times e, I know that k value, which is the natural log of 2 over 3 times t. So divide by c, so 3 is equal to e raised to the natural log of 2 over 3 times t. What's next? To solve for t, what's next? ln. So I'll take the natural log of 3 is equal to natural log of 2 over 3 times t. So now to solve for t, I'm going to have to divide by that particular k value. When I divide by k, that's the same thing as multiplying by the reciprocal. So t is going to be equal to the natural log of 3 times 3 over natural log of 2. So what's my answer choice then going to be? A. Okay? So like I said, these could be calculator or these could be no calculator questions. So any questions on these 3 examples? All right, last problem. I noticed the directions say this is a no calculator question. So they're telling me that P of t represents the number of wolves in a population at time t years. The population P of t is increasing at a rate. So what does that tell me that they're giving me? They're giving me what? Increasing at a rate. So in terms of calculus, what does that mean? They're giving me a derivative. Proportional to 800 minus P of t. So again, if you think about what we just talked about, the differential form of an exponential function, remember, is your dy dt is equal to k times y. So now again, I need to substitute what are they giving me in terms of y. They're giving me that function 800 minus P of t. So then again, instead of dealing with y's, I'm dealing with p's. So dp dt is going to be equal to k times 800 minus P of t. So any questions on how I've set that up? Because if you look at part A, if P of 0 is equal to 500, what do they want me to find? They want me to find P of t in terms of t and k. What are we going to use that P of 0 is equal to 500 for? They're going to use the initial condition. This is our initial value problem, exactly. So now I want to solve for P of t here. So what am I going to have to do with my variables? I'm going to have to do my separation of variables. So what am I going to do to separate these variables? What can I divide both sides by to get k by itself? I can divide both sides by 800 minus P of t. And then I can multiply both sides by dt. Because remember, I want to find P of t. What's next? Integrate. Well, integrating the right-hand side should just be kt plus c. What happens when I integrate 800 minus P of t? What's that going to give me? Negative ln, the absolute value of 800 minus P of t. If you think about doing a u sub, so again, because P of t is negative, so if I did a u sub, if u is equal to 800 minus P of t, my du would have to be negative dt. Now, before I exponentiate both sides of the equation, I want to isolate the ln. So what am I going to do to both sides of this equation? I'm going to isolate ln by dividing everything by a what? Negative. So that natural log of the absolute value of 800 minus P of t is equal to negative kt. C is still a constant whether it's positive or negative. Just remember, before you exponentiate and raise the entire equation to a base of e, you want to make sure that the ln is by itself. Now I'm ready to raise both sides of this equation to a base of e. So e raised to the ln is going to be 800 minus P of t is equal to e raised to the negative kt plus c. Or what's another way to write the right-hand side? Another way to write this right-hand side is going to be what? C times e raised to the negative kt. Now, it's kind of an eeny, meeny, miny, mo. We know we're going to solve for c. So you could either solve for c here, or you can solve for c after you get p of t by itself. That's kind of up to you in terms of when you want to solve for c. I'm going to go ahead and I'm going to get p of t by itself. So again, if I add p of t to both sides and then subtract, I'm going to have 800 minus c times e to the negative kt is equal to p of t. So now this is where I'm going to use that initial condition. P of 0 is equal to 500. This is where I'm going to go ahead and I'm going to solve for c. So I have 800 minus c times e raised to the negative k times 0 is equal to 500. Well, I know e raised to the 0 power is just going to be 1. So I have 800 minus c is equal to 500. So what's c going to be equal to? C will be equal to what? 300. So then p of t is going to be equal to 800 minus 300 times e raised to the negative kt. So there's part A. So any questions on solving for p of t? You guys go ahead and do part B for me. Now that you have part A, go ahead and find k for me, given that p of 2 is equal to 700. Hopefully we came up with k to be equal to the natural log of 1/3 divided by negative 2. Any questions on how I found k? Don't forget, guys, another way you may see this expression written. This is equivalent to negative 1/2 times the natural log of 1/3, which is also going to be equal to 1/2 times the natural log of 3. Don't forget, with those natural logs, there's several different ways using those properties of logarithms you may see the answers expressed. All right, so when you're checking your answers, make sure that if your answer doesn't match up, look at those properties of logs. All right, any questions on B? Last part, let's take a look at C, limits, your favorite. Find the limit as t approaches infinity of p of t. So again, I want to find the limit as t approaches infinity of 800 minus 300 times e raised to the negative kt power. Again, you can plug the k value that you found in part B in if you want to, but you can answer the question without doing it. So remember, property of limits, I'm going to take the limit of each term. So the question is, what's the limit as t approaches infinity of 800? 800. Remember, property of limits, the limit of any constant is just that constant. Now remember, what you want to do when you're looking at limits, you want to make sure that rewrite the expressions with positive exponents first before you're trying to decide what that limit's going to be. So I have minus 300. Getting rid of this negative exponent, it's going to be 300 over e raised to the k times t power. So I want to find the limit as t approaches infinity. Again, it's the t value that's approaching infinity. So 300 is a large number, but infinity, I can make that a much larger number. What's happening with this fraction, 300 over e to the kt, as t is getting larger and larger? It's getting closer and closer to 0. So the limit then of 300 over e to the kt, this is approaching 0. So then what's the limit as t approaches infinity of p of t going to be? That's simply going to be 800. All right, so any questions on 8.2? So like I said, guys, the quiz on Friday is just going